Grid, a digital frontier. I tried to imagine clusters of redstone signals moving through the machine. What did they look like? Boats, minecarts. Were the wires like highways? I kept dreaming of a game I thought I'd never see. And then, one day, I got it.
Hey there, Poster people. Today I'm standing in front of my first ever Minecraft arcade machine, and it might be the most ambitious redstone project I've built so far. This is a fully playable, reimagined creation of the Light Cycle minigame from the 1982 TRON arcade game, built entirely in Minecraft. Unlike most of my other game builds, this one isn't turn-based. Both players are moving at the same time in real time, just like an actual arcade game. The idea came after I watched the TRON trilogy, started learning more about the series, and ran across this old TRON arcade game. Then I started wondering, could I actually build the TRON Light Cycle game in Minecraft? At first, it sounded simple. 2 players, 2 directions, 2 colored trails that stay on the grid. Just a couple of shift registers with a custom display cell. Add some memory to remember where the lines are, and you're done, right? Well, not exactly. Some parts of this build came together surprisingly easy. Some parts took a lot of trial and error, and one specific problem ended up taking over half of the entire design time to solve, but I'm not going to spoil that yet. In this video, I'll walk you through the entire build process, the redstone circuits, the design decisions, and the solutions that made this machine possible. We'll map out the redstone flow at the end, so you can see how every circuit connects and how the whole system works. So let's enter the grid. To build the TRON Light Cycle game, everything starts with the grid. This is the space the light cycles move through, the digital arena where the entire game takes place. And from the beginning, I wanted this to feel like a faithful recreation, not just a loose interpretation. So I kept a reference from the original TRON arcade game on the screen the whole time, constantly comparing, adjusting, and trying to match the look of the original arcade game. Once the grid was in place, the next question was simple. What should the light cycles actually look like? I started experimenting with different designs, eventually landing on gold and diamond blocks to represent the bright yellow and blue. From there, I tested 2 versions, a 4-block design and a 5-block design. And even though the smaller one was cleaner, the 5-block version just looked right. I also made the decision to include the black section of the light cycle. Now technically, that made everything harder. Instead of tracking just 2 colors, I now had to deal with 3. But visually, it made a huge difference. And once I saw it, there was no going back. With the light cycles designed, my attention shifted to the display and how each cell would behave. My first idea felt pretty solid. What if every display cell in the grid was its own little module? A 3x3 display that would show either the body of the cycle or the trail it leaves behind. The concept was simple. When a signal enters a display cell, it builds the full cycle shape, and when the signal moves on, it leaves behind a line. To make that work, I added an extra circuit that would activate the wheel blocks on the adjacent cells, so that the cycle wouldn't just exist on one tile, it would extend naturally into the next one. So in theory, all I'd have to do is move the activation signal across the grid, and it would look like a single light cycle moving forward while the trail persists. Clean, simple, exactly what I needed, at least on paper. So I started building. Now to actually move the light cycles around the grid, I needed a way to send a signal in 4 directions. In other words, a 4-way shift matrix. This is not my first time building one, as I already made a few in past projects. So instead of starting from scratch, I went digging through my old builds to see what I could reuse. The first one I tried came from my Etch-a-Sketch machine. It was built on a 3x3 grid and is minecart power, because why not? 2 bidirectional shift registers combined to create 64 by 64 activation points across the matrix. And technically, it worked. But it didn't fit the way the system needed to be structured, because in this machine, I don't need just one shift matrix, I need 2. One for yellow and one for blue, stacked on top of each other. My plan was to pass the signals from the bottom layer up to the top so that both colors would align to the same display cell. That way, connecting everything to the display would actually be manageable. But the Etch-a-Sketch version didn't have room for that. So I went back to my other builds and pulled a different design from my Maze Runner machine. This one was built on a 4x4 grid, and more importantly, it had space to pass signals through, which made it much better to fit for what the machine needed to become. With the activation signals for both players now organized, the first system I could actually build was the collision detection. And this part was important, because without it, the whole game would fall apart the moment 2 light cycles crossed paths. My first instinct was to keep it simple, a counter for each display cell. The idea is, if a light cycle enters the display cell, the counter increases. If another light cycle enters the same cell, it increases again. And once the counter hits 2 inputs, that display cell triggers a game over signal, carried on the orange line across the system. At that point, I realized this wasn't just handling player collisions, it also covered trail collisions automatically. So the same logic worked for everything. But there was still one problem left, the edges of the grid. So to handle wall collisions, I extended the system by adding 2 rows and 2 columns to the shift matrices. These edge cells were calibrated so if a light cycle ever moved outside of the playable area, it would immediately trigger a game over as well. Now we have a way to end the game, but we also need to reset it. The pink line is the reset signal. It clears the counters and prepares the system for a new round. One important thing though, even with all of this running in the background, the yellow and blue signals still need to pass through the counter layer to reach the display cells. Speaking of display cells, that was the next challenge. And this one was far from anything I built before. In my previous projects, every display cell was its own separate module. Even in my recent Etch-a-Sketch machine, the cells could touch, but they were still independent. This time, they had to overlap, which meant some pixels weren't owned by just one display cell anymore. They are shared, and that completely changed how I thought about how everything had to be built. So I started simple. I built a version without worrying about space at all, just to get the logic working. And it worked. But it was 7 blocks wide. It needed to be 3. So I started compressing it. 7 became 6. 6 became 5. Then 5 became something that made me reconsider my design. At that point, I stepped back. I knew I could probably get it down to 4 blocks wide, but 3? That felt impossible. So instead of forcing it, I made a decision. Shift the entire design to a 4x4 display cell. I'm sure the door redstoners could compress this even further, but for this build, 4 blocks wide was the limit. And that gave me just enough room to work with, and it lined up perfectly with the 4x4 shift matrix. From there, it became a process of refinement, tightening the design, reworking layers, and a lot of what I can only describe as chaotic finagling. Change one piece of redstone, see what breaks, fix that, and break something else, over and over again, until eventually I had something that worked, and actually fit inside a 4x4 space. But even then, I wasn't done. Because this version worked on its own, now I had to figure out how it would behave when every cell was overlapping with the ones next to it. I cleared the prototypes and brought the display cell to the center, so I could start building the display wall. Because of the height of each cell, I couldn't just stack everything straight up. I had to split the display, half on the left, half on the right, just to fit as much as possible before hitting the build limit. In building, I already prepared the cells to be integrated horizontally. Vertically, not so much. So I started the simplest way I could, by smashing two cells together and seeing what broke. And surprisingly, I got a bit lucky. The top layer of one cell and the bottom layer of the next didn't interfere with each other. There was even a small natural gap between them that gave me confidence to move forward. That didn't mean it was easy. There were still bugs to fix, signals to reroute, but eventually I got a working version. So I started copying upward, layer by layer, and then I broke a whole section. One bad command and suddenly things weren't working anymore. I tried to fix it, but couldn't. So I moved to the other side and started again, and just kept going, until eventually I had half of the display built, the top cleaned up, and everything tied back to the reset system. At that point, I was feeling pretty good about the progress, so I called it for the night. But when I came back the next day and checked the map, something felt off. I couldn't tell what it was at first, just this uneasy feeling that something wasn't right. And then I saw it. The vertical integration was wrong, which meant this entire display wall wasn't gonna work. And there was no quick fix. I had to rebuild the whole display wall again. With a couple more hours of work, the display was built and working properly. The display is split with half on the left, half on the right, just to fit as much as possible before hitting the build limit. That's what formed this V shape. Now this next part got interesting. At this point, I had 4 inputs to work with: yellow position, yellow orientation, blue position, and blue orientation. But the display doesn't use those directly. It needs something more specific. I had to take those 4 signals and remix them into a new set of outputs: yellow vertical, yellow horizontal, blue vertical, and blue horizontal. Because after spending over 30 hours getting the display working, everything now had to match its logic. The solution came down to using 4 AND gates, each one combining the right pair of signals to produce exactly what the display expects. Simple idea. But fitting 4 inputs, 4 outputs, and 4 AND gates into a 4x4 space? That was anything but simple. For a while, I honestly thought this piece might be the one that kills the entire build, but I stuck with it. Iteration after iteration, adjusting the layout, shifting components, rerouting signals, trying to make everything fit within the constraints of the display, until eventually, I had something that worked. Cleanly, consistently, and most importantly, it fit. I am calling this circuit the signal controller. It connects directly into the shift matrix, and with that in place, the system is finally functional. At this point, the game technically works. The light cycles can move, the lines persist, the logic is there. But there's just one problem. There's no way to control it. Next up was the player input. The buttons themselves are pretty straightforward. They feed directly into the shift matrix. Behind the wall, those signals get grouped into 2 pairs, up with down, left with right. Those pairs are then combined to determine orientation. If the signal is on, the light cycle is vertical. If the signal is off, the light cycle is horizontal. Then both players' orientation is carried through the system on these gray and black lines. Then there's the reset. At the end of a game, everything needs to reset automatically. That starts with the orange game over signal, which hits the magenta counter reset line. then runs through this light gray redstone spiral, resetting the entire display. Now back to the controls, which went through a few iterations. I started with buttons, switched to pressure plates, and eventually came back to buttons using a design based on my Etch-a-Sketch build. In the final version, you'll actually see a mix of both, and I'll explain why later. Here is the important part. Player inputs don't directly move the light cycles anymore. Instead, they feed into the system as intent. The actual movement is triggered by the game timer. With inputs handled, the next piece was timing. Up until now, everything had been about what should happen. Now, I needed something to control when it happens. So I built a game clock. It's made up of a set of hopper clocks. The first acts as the activation pulse for the shift matrix, telling the system when to move the light cycles. The second controls the delay between those pulses, setting the pace for the entire game. In other words, this defines each tick, every movement where the logic updates and the display changes. Then, I brought the pressure plates back in. When both players step into position, they activate the purple line, the game start signal. That feeds into an SR latch, which starts the clock and begins the game. And once that was in place, the ending was surprisingly simple. The game over signal, the orange line from earlier, feeds back into the latch. So when a collision is detected, the clock stops, the game ends, and the reset is triggered across the system. But there is still one piece missing. How do the minecarts reset and start automatically? That's what these light blue lines are for. During a reset, the shift registers stay powered just long enough for the minecarts to run all the way to the end and loop back to their starting positions along this light blue rail. So every round, each light cycle begins from the correct starting position. That same signal also resets the direction selector in the controls, making sure each light cycle starts moving in the correct direction. The purple start signal that activates the game clock also pushes the minecarts onto the shift registers. So the moment the game starts, everything just works. Now that you've seen it in action, let's break down how it actually works. Each player sends 4 input signals into the system. Those first pass through the game timer, which controls the pace of the entire game. With every tick, the timer sends out the updated signals for both players, driving movement in all directions. From there, those signals are merged into a signal combinator, simplifying them into a binary state. And that's what gets passed into the signal selector. This is where everything comes together. The signal selector takes those binary signals and determines exactly what the display should show, blue or yellow, vertical or horizontal. At the same time, the game timer is feeding movement signals into the shift matrices for each player. The shift matrices handle movement across the grid and rely on a minecart return system to reset after each round. When the game starts, the start signal pushes those minecarts into position. As the game runs, both shift matrices feed into the collision detection system. If a collision is detected, it generates a game over signal that feeds back into the game timer, stopping the game instantly. That same signal also triggers the reset system, clearing the display, resetting all the counters, and returning the minecarts to their starting positions. And finally, the signal selector sends the finished output to the display cells, bringing everything together on the grid. So, how did I do with this redstone build? Rate the power of my redstone skills from 0 to 15 in the comments. If you want to share your own ideas, join the Discord and connect with other creators. What should I build next? Let me know below. And I'll see you in the next video, where we discover what's in box number 10.